Started. Okay, so today what we're doing is, well, we were talking about induction, and that was to prove a sequence of statements involving natural numbers, right? Well, now what we're going to talk about is how do you do variations? Like, what if I was asking you to prove a sequence of statements that are only true for odd numbers? For example, prove P of n for all odd numbers n. Well, then induction doesn't apply directly. You have to try some variation of it. Or what if, and remember our base case was always n equals 1. That's for a simple, straightforward induction proof. But if you have a proof where I ask you to prove P of n is true for all n bigger than or equal to 3, then you've got a different base case. N is greater than or equal to 3, right? I think a lot of people are asking or just wondering, tell me in the chat if you guys think this. Like, you're just wondering, how does induction work? Like, induction, it looks like magic, right? We assume what we're trying to prove and then we somehow prove it. Like, it's kind of weird, right? Is that what you guys think about induction? Can I get in the chat? Is that what you guys are thinking? Like, we just assume that something is true, and then is that kind of off-putting? Because if it is, I can try to explain it. Okay, let me try to give you a little explanation. What is induction? Induction is kind of like this. It's kind of like a recursive proof. And have you guys learned recursion in computer science? You haven't learned recursion yet? Okay. Recursion just means that to figure out the case of n, that depends on the case of n minus 1, right? Let's say for example, let's say that I'm trying to prove this. Let me make a sequence, right? And it's going to be this. I take the square root of 2, and then I take the square root of 2 plus the square root of 2. Then I take the square root of 2 plus the square root of 2 plus the square root of 2. And I keep doing this, right? Let's just say I do something like this, right? So I have a sequence of numbers. Let's call this first one A0. The second one will be A1. The third one will be A2. And in general, I'm going to have AN. Okay. Let's say I'm trying to prove something about this sequence of numbers. And so what can I conclude? I can conclude that the AN, satisfies a recursive formula. AN can be obtained from AN minus 1 by taking 2 and adding the square root of 2 plus AN minus 1, right? Look at this. This is A1, right? In this expression for A2 here, I have A1 inside it, right? And if I were to write down A3, if I wanted to, A3 would just be the square root of 2 plus A2. And if I wrote that out, it would be the square root of 2 plus this whole thing. And I have to erase my green arrow. See? So this sequence is recursive. Each term of the sequence depends on the previous term. Kind of like Fibonacci. Fibonacci, in each term of the sequence depends on the previous two terms. So this, in a sense, is a little bit simpler, except it has square roots in it. Okay, so you might notice something. If I plug root 2 into my calculator, what's an approximation for root 2? 1.41, yeah, and that's less than or equal to. So you might observe that A0 is less than or equal to. How about A1? Can someone quick math plug that into their calculator and see if they recognize? 1.84. So maybe I should have said that. A0 is about 1.4, which is definitely less than 2. And A1 is about 1.84, which is definitely less than or equal to, right? Maybe I should say even less than 2. It's actually less than. And I could check A2 if you want. 1.96, and that's definitely less than 2, right? So here's my claim, and I'm going to have to make some more space so that we can do this poll question later. Here's my claim, and I'm going to have to prove this claim that no matter where I am, I checked the first three terms, A0, A1, A2, but I didn't check A3, right? And if I did, I would have to whip out the calculator for this, right? Claim AN is less than or equal to 2 for all n. And the question is, how do you prove this? Okay. Let's say you didn't know induction. If you didn't know how to do induction, how would you prove something like this? Well, here, I could plug into my calculator this ridiculous number, but I don't want to do that. What I'm going to use is I'm going to use the fact I already knew. I already proved that A2 is less than 2, and I did that with the calculator. For A3, how would I prove it? Well, okay, this isn't part of the proof, but let's say check for A3, just to make sure the claim is true, because I observed it for 3 instances. How do I know that the next instance it's going to be suddenly false? A3 could be bigger than 2, right? Let's check real quick. A3, instead of plugging into my calculator this whole nonsense, why don't I just use the recursive formula, this formula here? A3 is the root of 2 plus A2. And I already proved that A2 is less than 2, right? I already proved that. So I can just say that I already know A2 is less than 2. So I know that this A3 is less than 2 plus, I can replace my A2 with 2, right? And now I just calculate. Root 2 plus 2 is root of 4, which is 2. So I proved it. A3 is less than 2, and I didn't use my calculator. All I did was look at the case I already had proven before. So how about if I wanted to prove this for n equal 4? What would I do in n equals 4? Same thing, right? I just make reference to the previous case. You see how my proof is recursive? Each step of the proof makes reference to the previous case. So A4 is going to be the root of 2 plus A3, which is less than the root of 2 plus 2, the same strategy, right? Same strategy. I already proved that A3 was less than 2, so I'm just using that. And that's 2, right? So as you see, it's not that I'm assuming that the proof is true for n equals 3. I'm not assuming that to prove the n equals 4 case. I'm not assuming it. I proved it. And how did I prove the n equals 3 case? Based on 2, right? Exactly. And so how would I prove? So, okay, I proved the 2 cases. How would I prove? Oops, I always do that stuff. My palm rejection not working. How would I prove it? Let's say I keep doing this, and I want to check for n equals 567, right? That means I've been sitting here for years just proving from n equals 4 all the way to 567, right? Let's just imagine that tons of time has passed, and I've proven all the way up to 567. What I would do is assume that I've already proven the previous ones. So supposing that I've already proven that a 566 is less than 50, sorry, less than 2, we can calculate a 567, and I get a 567 is equal to the root of 2 plus a 566 is equal to the root of, and by induction, basically, right? Because I know that I'd already proven the previous case, this is less than or strictly less than the root of 2 plus 2, which is 2. See? Okay, what I'm doing right now isn't the type of proof that you should be writing. I'm just showing you why induction works. I'm just giving you an example illustrating that induction isn't silly. Induction is about proving all the cases up to n and then using that to get the n+1 case. So in that induction hypothesis step, when I say suppose that you've proven an or proven p of n, I'm not saying just assume randomly. I'm trying to, what that step is saying, what induction hypothesis is saying is assume that, well, you've proven p of 1 and show that you can use p of 1 to prove p of 2. Show that you can use p of 2 to prove p of 3. Show that you can use p of 3 to prove p of 4. In general, what the induction step is doing is just saying suppose or show how p of n can be used to prove p of n+1. So that's what the induction step is. Induction step is just a generalization of all these. So in an actual proof, you wouldn't do all these. You would just do one induction step, right? So induction step means assuming you've proven the statement assuming you've proven p of n, show that p of n, show how p of n can be used to deduce p of n+1. It's not that I'm assuming p of n is true. It's that I'm showing that p of n implies p of n+1. Okay? That's what induction is. It's not randomly assume some random hypothesis. Okay? Everyone's getting it? Is that clear? Clear a little bit? I'm just saying that the proof is recursive. Induction is ultimately a recursive style of proof. That's what it is. And speaking of induction, there was a problem that we did that I didn't do last time. Does anyone have questions about the explanation I just gave? Okay, great. So let's go up here, way back above what I said earlier, and let's prove this exercise from last time that I didn't get to, okay? So prove that this sum of this weird thing, so this is a sigma kind of question, right? Equals this really simple expression, okay? So how about I give you 5 minutes to work on this, and then I'll try to take it up within 5 minutes, okay? I'll give you 5 minutes to work on this. Okay, let's take up the problem. Who wants to start me off on this one? Who wants to give me the first line of this proof? Base case, right? Base case, prove the base case, exactly. In fact, before you even do that, what should you do? Before you start proving the base case, what's the real way to write up the proof? Write down the terms, say proof by induction. Yes, exactly. Announce the way that you're doing it. If you don't say what you're doing, it's going to be that much little bit harder to prove or to read for the reader, right? So let's say proof by induction. That's all you have to say. Or we prove by induction if you want. Doesn't matter. Okay. And so then you're right, the base case. If n equals 1, then let's just check. What do I do? How do I check this statement for n equals 1? This equation. I circled two things, but I should have circled this whole thing. How do I check? I just plug n equals 1 into this equation, and I can do that. What I should do is check the left-hand side and check the right-hand side, right? So LHS, the left-hand side, is the sum from I equals 1 to 1 of 1 over 3i minus 2 times 3i plus 1. And I can just, there's only one term in this sum from I equals 1 to 1. So let's just plug in I equals 1. I have 1 over 3 minus 2, which is 1, times 3i plus 1, which is 4. So I got 1 over 4. And I check the right-hand side. If I plug in n equals 1 here, I get 1 over 4. 1 over 3 times 1 plus 1, which is also 1 over 4. So LHS equals right, RHS, and the equation is verified. Okay, not so bad. Now, let's do induction step. And remember, I'm going to write, assume that I've proven whatever, but remember, that's not really what's going on. What's going on is from the n equals 1 case, I just verified. I can use the n equals 1 case to check the n equals 2 case. Then I can use the n equals 2 case to check the n equals 3 case. Then I can use the n equals 3 case to check the n equals 4 case, and so on and so on and so on. But instead of doing that infinitely many times, which is impossible basically, instead of doing that infinitely many times, I'll just prove that in general, I can always get from the n to n plus 1. That's induction. Okay, so suppose I've proven, we've proven the statement for n equals k. So it would be this statement here, except with all the n's replaced by k's. Okay, then I have to erase our 20 questions. And I have to prove the statement for n equals k plus 1. So we prove the statement for n equals k plus 1. All I'm doing is setting up. I haven't really done too much math yet. We will prove the statement for n equals k plus 1, which would again be the same statement again, except I replace n by k plus 1. So here's an n. I replace that with k plus 1. And here are two n's. Let's replace those with k plus 1. So I need to make some space here. Whoops. K plus 1 over k plus 1. See? Okay. So, okay, let's do it. Okay, so let's just start on the left-hand side. So start on LHS. Or take this thing. And what's the first thing I should do? Split it up into two summations. Okay, which two summations? Split it. Partial fractions, no. We don't do partial fractions in this class. I equals 1 to k and 1 to 1, exactly, right? What I'd like to do is extract the k plus 1 term, right? Because if I do that, all that'll be left is the sum up to k. And I know something about the sum up to k. That's the induction hypothesis. That is the induction hypothesis. I know something about the k case. So why don't we extract the k sum? So let me just, in fact, I'll just copy it and add on the k plus 1 term, which is what? 1 over 3 times k plus 1 minus 2 times, I'm running out of space here, 3 times k plus 1 plus 1. And then I have 1 over that, right? This is the k plus 1 term. Sorry, this is the I equals k plus 1 term. And this is everything else. Everything up to k. Yep. So all I did was pull out the k plus 1 term. Okay. And now let's simplify it as much as I can. By induction, I know something about this sum by this formula here. I know that I've got k times k over 3k plus 1. So I know I've got k over 3k plus 1. And all I know is that this thing is a big fraction. So all I can do is simplify. Okay. All I can do is simplify this. And so let's try. It's going to be hell. K over 3k plus 1 plus, how do I simplify this? I'll just do it live. I have 3k plus 1 minus 2. So that sounds like 3k plus 3 minus 2. That sounds like 3k plus 1. And then this second term here is 3k plus 3 plus 1. So that's 3k plus 4. Okay. And then what do I do? I guess I should get a common denominator here, right? So why don't I multiply that by 3k plus 4, this missing term, 3k plus 4 over 3k plus 4, just to introduce the common denominator. That's how you add fractions. Okay, let's do it. 3k plus 4 times k. Okay, I think at this point, the induction part of the proof is basically good. Plus 1 all over 3k plus 1 times 3k plus 4. Okay. And now what I'm going to do is just keep simplifying, and just in the interest of time, maybe I'll omit all the steps there. But as you keep simplifying, you're going to get the exact thing that we wanted, which is where? This k plus 1 over 3k plus 1 plus 1. Okay, I won't do all the steps because this is just high school algebra at this point. And that proves the induction step, right? So this proves the statement. So the statement for n equals k plus 1 is proven. And then you say conclusion. The statement is true for all by induction. The statement is true for all n. That's the proof. Okay. So what I did was in fact, this is an important part. This is the most important part, basically, is I pulled out a term. And the reason I pulled out a term okay, I took this sum. I noticed there's I equals 1 to k plus 1. I took the k plus 1 term out, and all there's left is I equals 1 to k terms. The reason I did that is because I know something about this. That's the induction hypothesis, right? So I just applied induction. The place I got this bit was by induction hypothesis. That's how I got this part. Okay, which came straight from here. This formula. Okay, that's induction. This is one of the straightforward induction proofs where you just do it. Sometimes there's a big trick to it. A lot of the problems in the textbook have tricks to them, but this one doesn't have a trick to it. This is just straight induction. Okay. Okay, cool. So now let's get to those polling questions. And remember, we were talking about variations on induction. Okay, I have about 20 minutes left. So remember, this induction example that we just did had n equals 1 as the base case. And then to prove, remember, the base case is p of 1. And the induction step is proving that p of k implies p of k plus 1. Okay, if these two things are different, then you've got to use a variation on induction. Okay, so that's what I want to talk about here, is variations on induction. Okay, ready to go? Here's the first poll question. Let's say instead of proving p of n is true for all n, I want to prove for all even numbers n divisible by 3. What's the base case of this inductive proof? Okay, and for that, I have to give you the poll here. What is the base case for this inductive proof? Okay, let me give you a few minutes for this. Okay, so It looks like the majority answer was D, which is correct. Let's see why. How do you get the base case? How do you get the base case from for an induction proof? Usually it's just n equals 1, but if I change things, all even numbers divisible by 3, the base case is the smallest possible case, okay? The very first number, right? Base case is smallest possible case, yeah. Sorry, base, I meant to write base case. Base case is the smallest possible case. In this case, I need the smallest even number that's divisible by 3. That's 6, right? Okay. Smallest even number divisible by 3. Isn't that just the same as all multiples of 6? Yeah, I think it is. That is the same. Saying that an even number divisible by 3 is just saying a number divisible by 2 and 3, which is the same as saying you're divisible by 6. Okay. So it's all good. That's what you do. Cool. So let's go to the next polling question, just because I have one more exercise for you here. Well, actually, before I move on, are there any questions about this one? Oh, QP, could n be negative? Since we have negative even numbers, I see. In the context of an inductive proof, we basically assume we're working with positive numbers in the simplest cases. In this case, I meant to say even positive integers. But it's very common to just say even number. And even the word number, I should have said integers technically, I guess. I don't know, just to be clear. But yeah. Okay. Now let's go to the next polling question. I see a lot of questions in the chat. I'll try to see if you guys can answer each other's questions, just so I can move on here. Okay, so this polling question, I'll put up the poll, but don't start answering it until I read the question to you. Okay, this question says, if P of n is a statement, right, and I want to prove that P of n is true when n is a multiple of 5, what's the induction step? Okay, what's the induction step? Okay. Sorry, I didn't record that. The answer was C, and the reason was because the base case is P of 5, and then the next smallest multiple of 5 is 10, and then the next smallest multiple of 5 is 15, and then you increase by 5 each time, okay? Where K is a natural number. Okay, so that's the poll question. I have one more problem for you guys, unless there's a question about this one. Anything I can clarify about this problem? Ah, I see. Okay, there's a lot I could clarify about this problem. Okay. Okay, actually, in fact, there's two things wrong with the way what I just said. Yeah, I'm not happy about the way I just said that. There's two things wrong with what I just said and what I wrote on the page. The first thing is that there's a typo, and the second thing is that the correct answer is D because of the typo. Does anybody know where the typo is in D? No, it's not whenever. It's here. It's this P of 5. P of K implies P of 5. P of 5 is a single statement, just with 5 in it, right? That's not supposed to be right. That's just one statement. What should I have written? K plus 5. Good. K plus 5. Sorry about that, guys. I don't know why K plus 5 is what I should have written, right? So now it's looking remarkably like C. By the way, C isn't, if I put it like this, C definitely isn't right anymore. Okay. If it was P of 5, it would have just been some statement. The conclusion would just be true, right? That's definitely not the right way to do it. It's P of K plus 5. These two look similar, but think of it like this. In this statement here, I would have to prove that P of 4 implies P of 4 plus 5, which is 9, right? This statement here, if k equals 4, then this is just the statement that p of 4 implies p of 9, which is totally irrelevant to this sequence of implications that I'm trying to prove, right? I don't need the p of 4 case. That's not a multiple of 5. I only need to prove it p of k when k is a multiple of 5. And to get from a multiple of 5 to the next multiple of 5, I just add 5. So the correct answer is actually D because of that typo. The correct answer wasn't C anyways. I just forgot to notice this. K is divisible by 5. So this is actually not the right answer. D is the right answer. Okay. For each multiple of 5, get to the next multiple of 5. And Michael's asking what's wrong with B. Well, for example, if k in B, to get from k equals, for example, if k equals 5, that's obviously a multiple of 5, then the statement is p of 5 implies p of 25. And I've skipped p of 10, p of 15, and p of 20, right? So that's why B is wrong. Because you skip too many cases. You want to get from each multiple of 5 to the next multiple of 5. Okay. Okay. Let me see. Okay, I do have an exercise here, but we only have 5 minutes left. So let me do a different example like this. P of n is true when n is a multiple of 5, huh? How about if I wanted to prove this? Let's say I wanted to prove something like this. Here's another exercise for you. Let's say I want to prove P of k when k is a square. Okay. How should I structure the proof? This might help clear up some stuff. How would you structure a proof like this? If I'm trying to prove that P, maybe I should have said P of n, but oh well. In fact, actually, let me change it because we usually use n, not k, right? So let's stick to n just to keep things simple. Define what is a square. Yeah, what is a square? What do I even mean by that? Shouldn't k be a natural number? Squares are four-sided objects. That's not a number. What do I mean by square? Perfect. It means root k is natural. Yeah, you could say that, but I think it means instead of saying it like that, remember, we shouldn't take square roots. That's a real numbers operation. When you're working with integers, try to pretend that you're talking to someone who doesn't know what a real number is. That means they don't know what a square root is. I would write it like this: n equals k squared for some k. That's what a square is. So some examples of squares would be 1. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. Sequence of squares. Okay, right. Okay, some people in the chat are getting it. So what you would do is you would start with the base case, and you would start with the smallest possible square, right? So n equals 1. So prove the problem when n equals 1. So prove P of 1. That would be the base case. How about the induction step? How about, in fact, let's break it down even further. What's the induction hypothesis? Or yeah, let's just say induction step. What's the induction step? Well, you suppose that you've proven what? P of some square. And what I want to get is the next square. How do I get from 4 to 9? I add 5. But then how do I get from 9 to 16? I add 7, right? And then how do I get from 16 to 25? I add 9. So something's going wrong, right? Each step depends on the previous step. or sorry, each step is not the same amount from the next step. Like from 4 to 5, that's from 4 to 9, that's 5. From 9 to 6, that's 7, right? So suppose we've proven P of k squared. Yeah, exactly. What we have to prove is the next square. So we must show P of the next square. Like this. Another way you could say is to get from one square to the next, you add an odd number, but I think that might take a little bit more work than just doing this. This is a bit more simple. This is what you would do. So as you can see, I just went from k to k plus 1, which is just normal induction, right? So I think a better way to do a lot of these problems is just write the n out as whatever the thing you want it to be is, right? To write it out as a square and then do induction on that parameter. In this case, I wrote n as k squared and then I just did induction on k, ordinary induction on k. So even in this problem where I want to prove P of n, where n is a multiple of 5, here's an alternate way to do that. To prove P of n when n is a multiple of 5, there's two ways. One is the way I just said in the poll question, right? One would be this way. Prove the base case P of 5. Whoops, sorry. Let me move that over a little bit. One way would be to prove the base case P of 5, then prove this induction step. That you can jump up by 5. But I think maybe a better way to do it would be to express in a different form. Say, let's prove P of 5 k for all integers k. And use normal induction. By normal induction. Right? I think this way is actually better, because what's the base case now? It's still the same. It's k equals 1. So meaning I have to prove this statement P of 5k when k is 1. So prove P of 5. So it's the same, as you can see, it's the same base case. And then for the induction step, prove P of 5k implies P of 5k plus 1 for all natural k. Okay, so I think I like this way a bit better, because this way, if you interpret it this way, it looks like a variation on induction, and it might be a mystery, like how did we get that, or like what if instead of saying n was a multiple of 5, I said something like n is a square that's a multiple of, like, I don't know, 53. Like what if I said something like that? Then it would just be a bit more messy, right? I think it's easier to convert the number you need, n is a multiple of 5, just convert that into saying that n equals 5k and then do induction on a normal induction on k. I think that's actually a lot more straightforward. In fact, that is what I usually do. That's what I personally do. I just do normal induction on k. So from k, so my base case is k equals 1, and my induction step goes from k to k plus 1, just like normal induction. So that's personally what I do. Okay. I think it's a bit simpler. Okay, so that's it for induction today, guys. I will see you on Wednesday.